Everyone. In this video, we're going to start off by talking about aromatic substitution reactions. So last quarter, we talked about aromatic compounds and what defines an aromatic compound and the fact that aromatic compounds are very stable. So if you have a molecule like benzene, which is aromatic and very stable, it can be difficult to perform reactions with that molecule. So we're going to learn how to add functional groups to a benzene ring. And you can see in this reaction map, there's actually quite a few reactions that we can perform here. So these reactions are called electrophilic aromatic substitution reactions, or EAS. And we're going to cover quite a few of them in this chapter. But let's just start off with a discussion of the stability of benzene. All right, so we know that benzene is aromatic. And we previously discussed how if we try to do a traditional addition reaction on benzene, let's say to form the following product, it just does not work. And why doesn't it work? Well, let's look at our product, our hypothetical product. Is that an aromatic compound? No, it's actually non-aromatic. So we're breaking the aromaticity of benzene by trying to add these bromines, and it's just energetically not favorable. So this reaction does not occur. So let's just make a couple notes. So here we would be destroying aromaticity, and it's energetically unfavorable. Now, there is a way to add bromine to a benzene ring, but we would need a catalyst. And remember, catalysts just give a different pathway with a lower activation energy. Okay, so if we start with benzene again, we're going to try to add bromine to the ring, but this time we're using a catalyst, iron tribromide. And the product we end up with only adds one bromine to the ring. But notice that it's still an aromatic compound. So this is one way that we could add a halogen to our benzene ring. All right, so let's look at the general mechanism for this type of reaction. And this will be pretty similar to all of the reactions that we're going to discuss. Okay, so we're going to start again with benzene. And benzene is going to be a weak nucleophile. So remember, nucleophiles are electron rich, but the reason benzene is a weak nucleophile is due to the fact that those pi electrons are actually delocalized around the ring. And benzene doesn't really want to react necessarily because it's so stable due to its aromatic nature. So that means that if we want to add something to benzene, it has to be a very strong electrophile. And we'll just symbolize the electrophile as E+. All right, so benzene's going to attack that electrophile, and we're going to end up with an intermediate. All right, so this is called a sigma complex, or you could also call this an arenium ion. All right. Now, remember, in our reaction, we ended up forming an aromatic product. So, in our mechanism here, we have to show how we're going to reform that aromatic compound. So, in the next step, we're just going to use some sort of base to grab onto that proton on the ring. And then the shared electrons will form a pi bond. So we're re-establishing that aromaticity. And we're also forming the conjugate acid of our base. All right, so this will be the general mechanism for, again, all of the reactions that we're discussing here. So the electrophilic aromatic substitution reactions. Okay, so let's look at halogenation. So we already said that if we want to add bromine to benzene, we're going to use Br2 and the catalyst iron tribromide. Oh, catalyst, there we go. And that's going to form this product here. Now, just a note about iron tribromide. Iron tribromide is formed by reacting 3 bromine molecules with 2 iron atoms, and that will give us 2 iron tribromide catalyst molecules. Okay. Now, we could also add chlorine to the ring, but we'll need a slightly different catalyst. So let's say we add Cl2. The catalyst we'll use here is aluminum trichloride. And that will add chlorine to the ring. So unfortunately, we can't do this with fluorine or iodine. So we can't use F2 or I2. And you might remember from last quarter and maybe even the quarter before that, I forget how far back we talked about this, but fluorine generally reacts too violently and iodine reacts too slowly. So it is difficult to do these reactions with those halogens. There is a way to do it, but we'll learn about that later. Okay, so now let's look at the mechanism. So we're going to kind of look more closely at that catalyst. So let's look at iron tribromide. Let's see why it's an effective catalyst. So we're going to look at iron tribromide kind of from the side. So iron tribromide is actually a good Lewis acid because it has an empty p orbital, kind of like boron. And let's use a different color to draw that p orbital above and below. So if we add Br2 to our system, remember we have a bunch of lone pairs here. So one of those lone pairs from one of the bromines can actually donate into that empty p orbital. And what we end up forming is an adduct. Let's see, so I'll just draw this a little differently here. So we've got our 3 original bromines, and then we'll also add in Br2 on the side. So iron becomes negatively charged. Bromine that's attached to iron becomes positively charged. Now, if we're thinking about electronegativity, in general, electrons are kind of flowing this way towards those 3 bromines on the right-hand side. So this bromine on the very end is partially positive as well. And it's more easily accessible than the other bromines. So what will happen is the benzene ring is going to attack that partially positive bromine, and then we'll leave electrons behind on the other bromine. There's a lot of positives and negatives going on here, but hopefully it's making sense. And we end up forming that rhenium ion, or that sigma complex intermediate. Oops, I guess my Apple Pencil is dying. We'll have to make this quick. Okay, so now that we've lost a bromine from our catalyst, we have FeBr3 plus that extra bromine, and I'll highlight that in purple just so we can keep track of our bromines there. And this is going to act as a base. Oh, I forgot my negative charge on iron. So bromine is going to grab onto the hydrogen on the ring, and we're going to leave behind pi electrons. And then we get our final product. Plus, our catalyst is going to regenerate because we lost that purple bromine, so we reformed iron tribromide. And we also formed HBr, so the conjugate acid. All right, so now let's look at chlorination. It's going to be very, very similar to this mechanism, but instead of iron tribromide, we're using aluminum trichloride. So again, we'll look at our catalyst from the side, and aluminum is a good Lewis acid here because it has an empty p orbital. So it can accept electrons, and in this case, it will accept electrons from chlorine. Oops. So this looks very, very similar, right, to the previous mechanism. All right, so again, benzene will come in and it will attack the chlorine on the end. And we form that rhenium ion, or sigma complex. And then our catalyst still has that extra chlorine on the end, and that's going to act as our base and grab onto a hydrogen. We'll leave behind electrons there and reform our aromatic benzene ring. But this time we have a chlorine attached. And then we reform our catalyst, and we also formed hydrochloric acid. So basically the same exact mechanism, we're just using aluminum trichloride instead of iron tribromide. Now, one thing too is in our bromination mechanism here, instead of iron tribromide, you could also use aluminum tribromide. You really just need a good Lewis acid in order to do this reaction. So aluminum could take the place of iron there as well. All right, so I think we'll stop there today. Next time we'll cover a few more reactions. So we'll cover sulfonation, where you can add a sulfate group to the benzene ring. We'll also talk about nitration, where you can add a nitrate group. And we'll just keep going from there. So I will see you in the next video.